Hi. In this video, we are going to see what is a normal distribution, what are the visual and statistical tests you can apply to verify whether a data is normally distributed or not, and if a data comes from a non-normal distribution, what transformations you can apply to make it to a normal distribution. That's what we are going to check in this video. Now, normal distribution or Gaussian distribution, or sometimes even called the bell curve, is a symmetric distribution where most of the values are centered around the peak. If you see the green area, this is the peak. Or even the yellow area, most of this value, like 68% of the value is centered around the green area, and remaining 95% of your values is within this yellow boundary, right? So that's what your normal distribution is, and your outliers are typically distributed around the tails of the distribution, the red area or the further, right? And this outlier can be dependent on your business domain. In some business domain, even the first standard deviation can be an outlier. In some business domain, it can be a second standard deviation or third standard deviation, or even more than that, because depending on the domain, the data value range changes, right? In this case, if I say like second standard deviation, the bottom, what you are doing is you are basically having the mean where the peak is, and then you have your standard deviation on the left hand side and the right hand side, right? You have the first standard deviation, second standard deviation. In this case, maybe the red is an outlier, so we can name anything more than two standard deviation can be an outlier, or it can be even three standard deviation. So this is how your normal distribution typically looks like. But most importantly, not all data that we see today is normally distributed, right? While every distribution is not expected to be normal, but some statistical test expects data to be normally distributed. Like if you take a t-test or Anova, or even the residuals of your linear regression are typically expected to be normally distributed, right? Now the data can come from any distribution, right? You have normal distribution, log normal distribution, Weibull, exponential, logistic distribution. It can be any distribution. You can apply statistical tests that are applicable to that distribution, but if you want to apply a statistical test that is expects the data to be more normal, then you can apply some transformations to it to make it more normal. And in case of a normal distribution, typically the mean and median are equal. As I said, it's typically equal. Now sometimes it may not be perfectly normal. You can still apply those statistical tests, and in that case there may be a slight deviation between the mean and median, and it's very common, right? And the main thing is you can apply an empirical rule that is available. If you see, this is the rule, like 68% of data lies within the first standard deviation. The 95.95% of data lies within the second standard deviation, 95.4. I'm just rounding it off. And 99.7% of your data lies within the third standard deviation. So you can apply this empirical tool, find out your values or probable values based on this distribution if the data is normally distributed. Now it can be typically challenging to identify whether the data is normally distributed or not, in the sense like your graphs can be sometimes deceiving, and sometimes when you go across a statistical test, you may be confused whether this statistical test is applied or not, and that's why like kind of it's a bit scary. But said that, let's see like how we can identify it with proper visualization technique and also statistical test, right? So let's see how to do it. So I'm going to add this code in Python, and what I'm doing is I'm using pandas to import my data set that I'm going to use to demonstrate it. I have for visualization, I have Seaborn and Matplotlib, and I have the SciPy stats package to run some statistical tests that are available to test whether the data is normally distributed or not. So I'm going to run this. I'm going to import a marketing data set. It's a insurance marketing data set. So I'm going to talk more about the data set. I'm going to use only few columns out of it. This data set is available in my GitHub repo. You can go and download it, or you can just give the same URL in your pandas data frame to basically import it, right? This is how my data looks like. It has information about the customer, which is nothing but a unique identifier. You have information about the state where the customer is, what is the customer lifetime value, what is the coverage he has taken. It's an insurance data set. I said there's the insurance coverage, what is his income, what is his monthly premium, what is the last, when did he make the last claim, and there are a lot of other data that is available over here: total claim amount, average vehicle age, whether the vehicle class is two-door or four-door vehicle. So there are a lot of data available. I'm going to use few columns. I'm going to use the average vehicle age, I'm going to use the customer lifetime value, and talk about different distributions and what transformations you can apply. Right, the transformation part can be scary, but there is an easy way to identify what transformations you can apply to make the normal non-normal data into the normal data. So let me quickly print about the info about the data set. You can see like these are the different data types, and none of this has null. So the non-null column is 6817. There is no null data. Almost everything is non-null. I can also quickly print summary about the data set. How many rows and columns? You can see basically I have 6817 rows, which is the shape. You take the shape object. The shape of 0 is the row and shape of 1 is the column. And then I'm printing the column name, and I'm also checking if there's a missing value or not. And the missing value is false. Right? I can quickly generate the summary statistics of this particular data set. So it will take all the numeric column and give you a summary statistics. And if you quickly visualize the summary statistics, you can basically say like the first column that we are going to take is the average vehicle age. And here you can see the mean, that is mean and the median. The second row is the median, and the first row is the second row is the mean, and the 50th percentage is the median, that is 50 and 50. And you can see in the average vehicle age column, the 50, it's both mean and median are pretty close. Right? This looks like a normal distribution, but let's go and visually inspect it. Right? It is not necessary that if the mean and median are same, it's going to be normal, but let's go and visually inspect it. So for the first thing I'm going to do is I'm going to use a distribution plot. And what the dist plot does, it plots a univariate distribution of the observation. And from the marketing DF, I'm taking the average vehicle age. And then if you see over here, this is how my data looks like. And if you see, the data looks like it's normally distributed, centered around the mean of 50. That's what it looks like. Right? Now, this is one way of visually checking whether the data is normally distributed. Right. Now, the second way is you can also have an quantile plot, and this is the quantile plot, and this is a probability plot, which is more like a graphical methods for comparing two probability distribution by plotting the quantiles of the underlying data. And if you see, basically the red line over here is your reference line, and basically you're plotting your different quantile values on the red line based on your data. And I'm using the same column, average vehicle age. And if this particular data falls close to your or on top of the red line, the data is assumed to be completely normally distributed. But it can also deviate completely from the line, which we'll show in the next example. Right here, it seems to be normally distributed, while some of the points are not falling in the red line, but that's fine. Right, as I said, there can be some deviation per your business rules that you can allow if you are running some test that depends on normal distribution. Right, this is the second way. The third and easy way to do is box plot. Right, we know like box plot typically does it. And if you see, like what I said is your normal distribution is a symmetric distribution, and the box plot, if the center part is the mean, and here is the 25 percentile, that is the Q1, the quartile 1, the quartile 3 is there, and this is the interquartile range. And if you see, like the mean, the both side of the mean, the minimum value and maximum value looks more symmetric. Right now, this is just a visual. Right now, we still don't know whether it's normally distributed, but from the visual you can get some perspective on how the distribution of data is, what are the outliers in this case, and everything you can get. Now, let me go back and run some statistical test to verify if this data is normally distributed or not. So what I'm going to do is, the very first thing, I am going to run the normal test. And the normal test is basically, it's going to test whether a sample differs from a normal distribution. So the null hypothesis is the data came from a normal distribution. And the alternate hypothesis In this case, if the p value is less than 0.05 or whatever threshold you said, it's unlikely that the data came from the normal distribution. So for that, I'm using the stats package. In the stats package, there is a normal test function, and I'm just passing this value, right? And it will give me a chi-square statistics and a p-value out of it. So once I run this, it will give me both of it, and in this case the p-value is greater than basically 0.05. That means our null hypothesis is true. The data is coming from a normal distribution. This is one way of checking it. There are a lot of tests available. There are plenty of tests available to check whether a data is normally distributed or not. I'm just showing few tests over here. The next test that we are going to see is the Anderson-Darling test, right? The Anderson-Darling test is used whether to test if a sample data came from a population with a specific distribution. Now, Anderson-Darling test can be used for any distribution, but when you are specifying this particular statistics, you can specify which distribution you are checking against. And here I am checking against distribution equal to norm. You can even check whether it's a log normal or variable or exponential, whatever it is. You can check against the distribution. In my case, I want to verify whether this data came from a normal distribution. And for that, the null hypothesis is the sample is drawn from a population that follows a particular distribution. In our case, it's the normal distribution that I'm testing against. And the alternate hypothesis is data did not come from a chosen distribution, right? So once I run this, what it is going to do, it's going to give me a bunch of statistics, right? And in my case, the critical value, if you see over here, if you go over here, it's the significance level is, this is like basically your 5% significance level, 2.5%, 1%, 10%, and 50%. As usual, we will take the 5% significance level, right? That is like 0.95% probability, right? So this 95% significance level is 0.787. And if you see over here, this particular statistics is less than this value. That means our null hypothesis, again, we accept the null hypothesis, and the sample is drawn from population that kind of follows a particular normal distribution that we are given for. This is the second way of doing it. Now, assume like our data is not normally distributed. We can apply some transformations like log, power, or exponential transformation to make it normal. Now, how do you know which transformation to apply to make it to normal? And for that, what we are doing, we are using a Box-Cox transformation from the SciPy stats package. Now, a Box-Cox transformation is a transformation of a non-normal dependent variable into a normal shape, right? And as I said, normality is an important assumption for some of the statistical techniques. If your data is not normal and you want to use that statistical techniques, right? While you can use other statistical techniques that is applicable to your distribution, but you want to do apply that specific which expects data to be normal, you can apply a Box-Cox and you can run a broader number of tests using that, right? So in this case, what it's going to give me, it's going to, like, I'm just importing, I'm calling this Box-Cox, and I'm going the average vehicle age, right? And it will give me two values. One is the transformed value itself. It will automatically transform your value. You can take that value, which will be normal, but I don't want that, because I don't want what the statistical package give me. I want to understand what function I need to apply in my process to make it normal, right? So I'll be more interested in the lambda value. That is the second value that I'm calculating. So once I run this, it will give me a lambda value. Now, once I have a lambda value, a normal distributed data will have lambda value of 1, which is true in our case. We have visually seen that, we have statistically proven it, that our value is normally distributed. Now, in this case, if you see 1, then my data is normally distributed, then I just apply as is, right? But in case if the lambda value is different, this is the transformation table that you will apply. If your lambda is a negative value, right, then just apply 1 to the 1 divided by basically the input value to the power of the lambda. Make it just absolute value, make it a positive value, and apply it. It's 1 divided by, that is the inverse of the input value to the power, right? Now, if it's -1, anything power 1 is the same value, right? That's why I just put input. But think about it, you are just applying what it comes over here, input to the power of that value. If it's minus 3, just input to the power of 3, and similarly like that. And if it's zero point 0.5, zero point 0.5 is nothing but your square root transformation, right? So you are, since if it's a value is negative lambda, you will apply the 1 to the power of that value. If the value is positive, then you apply basically the direct function like square root. You don't have to do 1 divided by, right? And that's what you're doing. And if it's 1, it's this normal distribution as is. And if the value is 0, then you apply a log transformation. It's very simple to remember. If it's negative, then 1 divide by just the value power, and anything power 0.5 is nothing but a square root, also you can write it, right? And similarly 0 log, and anything positive you can just apply, you can just power it off directly with the input. This is the transformation table. Now let's take one more column, which may not be normally distributed, right? That's what I'm going to do over here. So the very first thing I am going to do is I'm going to run the same QQ plot. This time I'm taking the income column over here, right? And let me run this. And if you see over here, there are a lot of values that does not fall in the reference line for us, right? Which does not, it looks like the data is not normally distributed. I can run a box plot as usual like we did, and then quickly verify it. And if you see this data, basically that is the right side, it's more towards the right side than towards your left side, right? So there is some kind of non-normality in the data, looks like, right? Now I can again do my dist plot and verify it. And if you see the dist plot, if I'm drawing an basically normal curve, looks like that is there are a lot of data towards the right. It's not normal. Now I can verify with the statistical technique like we did. I'm going to use the Anderson-Darling test. And once I run this Anderson-Darling test, it says my statistical test value is 94, which is greater than my significance level of 5. Which is 0.787, right? Which is absolutely greater. So this shows our data is not coming from the normal distribution. In this case, like we kind of reject our null hypothesis. That's what we do, and we kind of tend to like kind of accept our alternate hypothesis, right? So that's what. This says it's not normally distributed. Now I can run my Box-Cox to get my lambda value to see like which particular transformation I need to apply. And now if you see the y is 0.44, it is close to 0.5. I can apply a square root, or I can directly take this 0.44 and then just power it off. All right, so I get the exact value. So now what I'm doing is I'm again going to the dist plot, but this time I am using the income column and applying an lambda function, and I'm telling numpy dot power, right? That is my input value dot power. It's a positive, so I'm just applying directly. It's not like if it's negative, I'm going to say like 1 by this value, but it's a positive value, so I'm just directly applying that np dot power. The x is my input value, and to the power lambda, right? If you see over here, that's what I'm talking about. Take this value and whatever comes in, just apply to the power lambda. Even if I apply 0.5 to the power lambda, it will automatically be square root, right? That anything like 0.5 power is going to be the same value as a square root of a function. So basically, if you see over here, that's what I'm doing over here. I'm just taking that function and applying it to the power. Now let me run this and let me see visually. Now you can see basically the data is kind of moved from your left and the data looks like centered, but still in the visualization I can draw a normal curve and it might come close to normal distribution. But this particular plot does not give me that whether it has got transformed or not. I can go back and again apply a Box-Cox transformation with the same function that I have created, and let's see like what the Box-Cox says this time. It says the second value is the lambda value. In this case, it says is 1, which shows that the data is kind of now normally distributed, right? And this is what I said. The other value you can directly use. It is a transformed value which Box-Cox does it for you. But when you are applying outside, you exactly want to know what function you are running. That's why I'm manually doing this function. So this is the function. This is one which looks like it's normally distributed. Now let me go to the third one and see for the CLV, that is the customer lifetime value. So in this case, I am going to print the customer lifetime value, and this shows that the box plot has heavy right tail, right? Some customers, there are some customers who are pretty high value, but most of the customers are centered around the mean of something close to 8,000 or whatever it is. But there are customers who are pretty high lifetime value as well. Now let me do a disk plot as well and see how it is. And you can see the disk plot also says, you can see this is what it is, and it is completely towards the completely a right tailed there's a right tail skew over here, right? Let me run the Box-Cox on top of it and let me get the lambda value. And in this case, the lambda value is negative. So when it's negative, I need to apply an inverse function, right? 1 by whatever the function I want to apply. So in this case, what I'm doing is I am taking the distribution plot. I'm just doing applying the same lambda function. I'm doing 1 by n to the power and x, and I'm doing an absolute value. This is very important, because if we pass the lambda value as it is, it will become like power x of negative minus 0.36. But you have to make it like a positive value. That's why I'm applying an absolute, and I'm passing the L value. That is the lambda value that I have it over here, right? And then I am going to check whether my data is normally distributed now or not. And it looks like the tail has completely gone and the data has some kind of centering. Still, it's not perfectly normal maybe, but the best way to check is go and again apply Box-Cox transformation and see how it looks like. Now, when I run a Box-Cox transformation, if you see it's close to 1.99999. It's close to 1. So our data, this is a transformation we have applied to make the non-normal data to normal, right? And remember this table. This table is pretty easy to remember. This is what you need to do when your data is non-normal distribution, and if you want to apply some statistical test which expects the data to be normally distributed, then these are some transformation functions you can apply to make it normally distributed. So that's about it. Thank you very much.